record. Okay, and then put the recording time and say, nice. All right. Hey, question on lab. All right, go ahead, Hunter. What's your question on lab?
So I'm doing just the first part of lab right now. I've had to kind of like piece it apart. But
hang on just real quick. This week is specific heat and
heat and fusion.
Yeah. Okay. Good. Okay.
So yeah, right now the first part of it, we're basically going ahead and we're taking a bunch of initial readings off of like the mass of the calorimeter or temperature calorimeter, all that. And we're supposed to find the specific heat. I went ahead and I algebraically isolated the specific heat of copper and set that equal to an equation. Toss all the data into a spreadsheet. That way it's easier. But I'm not getting anywhere close to the 0.0092 calories per gram. I'm getting for the first set of results, I'm getting 0.079, 0.08.
0.079 is about normal. I think it's a 79 something. That's what I got, which rounds to like a 0.08, right?
Okay, yeah. I think I was just I was just looking online and they said 0.092, and I guess that must be wrong. If that's the readings, then I'm actually doing it fine.
Yeah, you're fine. I probably should have said something more about it. It's amazing how much heat can actually leave the copper, just for how quickly I moved it from the hot water over. It has evaporating cooling on it very, very quickly, and that is a quick process. And so that's why it's one of the discussion questions. It says, what happens if there is a cooling process while you bring the metal over? And we've always gotten in that area of 0.08.
Okay, cool. Yeah, I haven't gotten to the end of it quite yet, so I probably would have seen that, but cool. Yeah. That was just my question at the moment, so thank you.
Yeah, so you're doing fun. That and I should point out that when you get into the heat of fusion, the accepted value is, and we're doing calories on that one. So the accepted value is 80 calories. But we tend to always get numbers like 70 calories or 68 calories.
And that just has to do with like the lab procedures and
in that case, I think it comes from when you are putting the ice in, the surface of it, I think, has already broken the bonds. They're already wet, and even some of them ones on the inside are actually kind of already broken.
Okay.
So get true measurements, and again, that's one of the questions. Also, is like, okay, what happens if?
Awesome.
So we always get low numbers on this, and I probably should have said more in the video that students always kind of panic a little bit before the lab's over and say, wait a minute, am I doing this right? It's low. Yeah. Yeah, just the nature of our equipment.
Cool. I'll keep that in mind when I go ahead and finish it. Yeah, thanks.
All right, maybe I better write my little notes here. All right, so let's go on there. All right, so chapter 21, number 20. All right, so at 10:11, chapter 21, number 20. Very nice. Okay. And let me put that on my paper here. Chapter 21, number 20. And I'll look that one up, but let me get my phone unlocked here. Okay, good. And let me display, turn it to never. Okay, that'll be good. Right, and then all right. My video camera going. All right, so now I think I can share my screen here in my phone. And then I gotta Do the screen monitoring. Okay. Oh, good. That was a fast response. That's a good sign. So now it's circling around here. Meanwhile, let me come over here and find the questions and scroll on down. All right, so chapter 18, 19, 20, here we go. All right, then, so finally into this week. All right, so 21, number 20. Is that what I wrote down? Okay, good. It's under the category of adiabatic. Okay. Now, let me just emphasize that hopefully what you've got out of this reading and me talking about it was that what makes this thermodynamic process challenging is every process is a little different. And because of that, we have formulas that say like heat and work, but they're unique to that process. We call this a path dependency. And so we got to be careful what kind of process do we have. There's a lot of processes. 4 of them, we like to give special names to them. This one is under the category of adiabatic, so I would assume it is going to be an adiabatic, but so let's just read it. So it says here, air, which is a diatomic ideal gas, at 27 degrees Celsius, an atmospheric pressure is drawn into a bicycle pump that has a cylinder of inner diameter of 2.5 centimeters and length 50 centimeters. All right, so maybe it looks something like this. A little bike pump has this piston in here, maybe even a double piston just to keep, anyways, and then has a kind of a T-handle up here. I guess it's got kind of a thin wall on it. The big thing here is it has an outlet. Maybe I should put a valve of some kind. Let's put a rubber valve inside the metal chamber. That's an ugly looking picture there. All right, but nonetheless, when somebody pushes down on all these molecules in here, they get compressed. They go and open up that rubber valve, and then they go out this hose that presumably is connected to a tire or something you're trying to inflate. This, I think it's a bicycle pump, so I'm going to assume we're pumping up a bicycle tire. But it says here the downward stroke is adiabatic. Okay, so they're telling you something real important here. The phrase adiabatic means there's no heat that can go in or out. Clearly, you're doing work on it, so you're pushing it down. So the change in internal energy, which is the work plus the heat, would mean that the change in internal energy is just related to the work pushing down. And so that's, I guess I could say this first line is the general principle of the first law of thermodynamics, the conservation of energy. And then this second one is unique to the adiabatic process, because the adiabatic process is the process that no heat flows. And there's a couple reasons that can happen, but one of the obvious reasons is you do it fast. And so in the process of doing it fast, you don't give them any time for energy to flow. Okay. Although there's some other interesting things about too fast, but that's a little beyond the scope of this semester. So let me not say anything more about that. I'm just going to confuse you. Enough to get started with our introduction to thermodynamics here. Okay, so the downward adiabatic compresses the air, which reaches a gauge pressure. Okay, so pressure, I'll call it sub G for gauge at 800 kilopascals. I lost my place here. Before entering the tire. Determine A, the volume of the compressed air, B, the temperature of the compressed air, and then C, what if the bike pump is made out of steel and has an inner wall that is 2 millimeters thick, assuming a 4 centimeters of the cylinder's length is allowed, to come to thermal equilibrium, blah, 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 blah. Okay, so C's a little more complicated here. Let me hold off on C, but I'm gonna start here with A. A says, what is the volume of it? One other unique thing that hopefully you got, or we'll explain now, is that during the adiabatic process, and only the adiabatic process, I'm going to say it again, what makes some of these problems really tough to do is that how the gas behaves is highly dependent on, how you're compressing or expanding the gases. And it's because of that, we have to always kind of pause and say, okay, what kind of process do we have? And of course, because of that, we have to learn what processes is appropriate for what action. And so this is the adiabatic one. And so the adiabatic has, I guess I'll call this one property, because 0Q means the change in internal energy only comes from the work. So this gas is going to gain energy because it's being compressed down, not because heat is going in or heat is coming out. But the other neat thing about the adiabatic process was that there is a mathematical relationship between its pressure and its volume. The pressure times its volume raised to this factor of gamma, and gamma is the relationship between the molar specific heat at constant pressure and the molar specific heat at constant volume. That is a constant. So what we could do is something like this. We could say if you take the initial pressure and you multiply it by the initial volume raised to a power of gamma, that equals this constant. Now, they gave us enough information because they gave us the initial pressure and they gave us the initial volume and they gave us what kind of gas it is. So we know everything on the left-hand side of this equation. So we could actually solve for this constant. Although normally I say don't bother to solve for that constant, because in this case, when you compress it and you've got final pressure and final volume, that too is equal to that constant. So you might as well just kind of skip the intermediate step that is actually solving for the constant and just set the two equal to each other and then go from there. And in this case, we are looking for the final volume. They give us the final pressure, they give us the initial pressure, they give us the initial volume, and they indirectly give us what gamma is. So maybe I should write those out here. So the initial pressure, well, let's see. If I come back to the reading here, it says air at 27 degrees Celsius and atmospheric pressure is drawn in. So this is 101,300 pascals. Okay. Initial volume. Well, again, that's kind of given when they give us the inner diameter and the length. They're giving us, the dimensions of the cylinder. And so this is pi r squared times h. This is the volume of a cylinder. So I'll take the pi. Now the r, I'll switch over to meters here. But they said the diameter is 2.5. So I'm going to have to move it 2 decimal places and cut the diameter in half in order to get the radius and then square it. Okay. And then the height, looks like I didn't write it in my diagram. I meant to, but they said this was a length of 50 centimeters. Okay, let me write that as 0.50 meters. All right. So let me just do a quick calculation on that one here. And so grabbing my calculator here, I have the, actually, let me do the radius first here. 0.025 divided by 2. Okay. And I will square that. I will multiply that by a pi. I'll multiply that by 0.5. And I get this 2.45 times 10 to the minus 4 cubic meters. Now I'm kind of wondering if I just should have left it in cubic centimeters. Because you can see up here, I have a relationship that, you know, could be any units as long as they're the same on both sides here. So, but my default was good to go to cubic meters because a lot of times energy is asked and energy needs to be in joules, which has meters buried inside of it. All right, so there is my initial volume. Okay, so that's those two. Let's do the gamma. Now, the gamma is the relationship or the ratio between the molar specific heat at constant pressure compared to the molar specific heat at constant volume. And we can get these if we remember what's called the equal partition energy theorem. The equal or equipotential equal partition energy theorem says that the energy gets distributed equally if we're looking at a random event. And so this is where 1/2 of R comes into play for each degree of freedom. So I'm going to go back where it says here we have a diatomic gas. They said air, and they actually helped us out. You may not know this, but air is mostly nitrogen. 80% of the air is nitrogen. It's actually a hair under 80%. And a hair under 20% is oxygen. But both of those are diatomic. So we could say that something like 99 point something of the gases in the air are diatomic. Yeah, there is some carbon dioxide, and yes, there is some water, but really those are tiny, tiny amounts. All right, so being diatomic, we know that there are 5 degrees of freedom. That is something that looks like a dumbbell. Can I use for diatomic? Maybe I'll just use my pen here, but if I have a molecule at one end of the pen, or an atom at one end and the other, it could translate X, well, maybe I should do this way, X and Y and Z. Well, that's 3 degrees of freedom, and then it can rotate around 2 of them. The third one would be rotating around the axis of the pen, which isn't much of an energy. So not counting that one, we have 5 degrees of freedom. So the argument is that how do you get the molar specific heat at constant volume? You count the degrees of freedom. Each degree of freedom is 1/2 R. Okay, so this would be 5/2 R. And then the molar specific heat at constant pressure is 1 R above that. So if this is 5/2, which I'll just call it 2.5, if you add 1 to it, you get 3.5. Which, if it's okay with you, I'll write 3.5 as 7/2. See, that way the R cancels off, the half cancels off, and we get 7/5. And 7 or 5 goes into 7 one time, and then there's 2 left over. 2/5 is 40%. So there's the other important factor. What is gamma? All right, so we got initial pressure, we got initial volume, we've got gamma, and we actually have then final pressure. Now I'm going to have to go to a page 2 here for me to write down final pressure. But that was given in the problem. The problem said the final pressure, and here's where we have to be careful. It says it's 800 kilopascals read on a gauge. It's called gauge pressure. Now, gauge pressure has its good and bads. Bad is it doesn't tell you the complete total pressure. What it tells you is what the pressure is above the atmosphere. Because things like filling up a tire, if you have a car tire and it says fill it up to 35 psi, what's meant by that is 35 above the atmosphere. You know, a flat tire is zero. Now, it's not zero absolute pressure, it's zero gauge pressure. It has nothing above the atmosphere. And everything we're dealing with in terms of the ideal gas law is what I'll call the science. It's the absolute pressure. So from a science perspective, we usually want absolute pressures. Often from an engineering perspective, we want gauge pressures because we want to know what it is above the atmosphere. You know, if we have no pressure above the atmosphere in our car tires, it doesn't hold up the car. And that's what we're trying to do, is we're trying to put air in the tires to hold up the car. So gauge pressure, you know, has its, you know, usefulness, and usually when it comes to building something practical. So I call it more of an engineering quantity, whereas absolute pressure is the science behind where the pressure is coming from. And these equations are about the science. These equations are about absolute pressure. So I say all that because the final pressure then needs to be written this way. It is 800 kilopascals gauge pressure plus the atmospheric pressure, the 101,300. And that's easy to overlook. So this is 800,000 added to 100,000 makes 901,300 pascals. So there's the final absolute pressure. Okay, so finally now I can come back to that equation that I'm trying to solve with you. And that is, there is a mathematical relationship between pressure and volume that I'm going to exploit. And it looks like of these 1, 2, 3, 4, 5 terms, they've given us 4 of them and asked us to find the 5th. Okay, so now it's just a bunch of math. You know, it's, hey, I got an equation, got 5 variables. I know 4 of them, put them in. There's 1 unknown. All right, so I'm going to put it in. So going back to page 1 here, the initial pressure is 101,300. Good. The initial volume, we had 2.45 times 10 to the negative 4. The power of gamma, we said, was 1.4. The final pressure we just worked out to be 901,300. And I suppose if I put in my units of pascals and pascals, that's going to cancel. And you can see then my volume in cubic meters raised to a power is going to match this one. So I'm going to get an answer. In cubic meters. So what is my final volume? Now, I like to show students to do this kind of in 2 steps because I've just seen so many mess up with the exponents. So let me just get everything to the left, every number anyways, to the left, and my variable to the right, but still raised to a power of 1.4 before I make the final step and then get rid of the power and figure out what it's or what the volume actually is here. Because there's a neat little trick, but for some reason in the past, I've given students a little bit of trouble. So hopefully you won't have that trouble, but I'll also show you what I call my way of approaching it. And so that's to break it into 2 steps. But let me just put in the numbers here. So this is the 101,300, okay, then times the 2.45 times 10 to the negative 4 raised to a power of 1.4. Maybe I'll just hit enter at that point. Okay, then I'm going to divide it by the 901, 300. And I'm going to just write that down then as 9.89, and looks like it rounds to a 9, times 10 to the negative 7. Okay. Now, how do I get rid of this? And there's a couple ways. I prefer this one. I prefer raising both sides to a power of 1 over 1.4. 1 over 1.4. See, that way on the right-hand side here, as you know, probably remember from your Algebra 2 class, is that if you have an exponent raised to an exponent, you multiply them. And that's why if you raise it to a power that's its reciprocal, you're going to get a power of 1. And so that's how I like to get rid of it. So I like to come over here to the left-hand side and then just hit raise to a power of. And then if I just hit 1.4 and hit the reciprocal key, I just got 1.4 reciprocal. And I like that. This makes it real easy for me. That I can just, hey, I want to raise it to the reciprocal of 1.4. So 1.4 reciprocal. All right, and then I can just hit enter. All right, so this comes out to be a volume of 5.14 times 10 to the minus 5. And I've been doing things in cubic meters. So cubic meters. And I see the next part is going to be highly dependent on what we did all this algebra right. So I'm going to go ahead and go to the internet here and call up the solution. What was this, number 20? And see if we did A right. They got 5.15 times 10 to the minus 5. Okay, and I got 5.14 times 10 to the minus 5. All right, good. So we're in agreement with the volume. Okay. Moving on down to part B, it says the temperature of the compressed gas. Well, there's a couple of ways we can do that. I'm thinking maybe the easiest way here is to remember that pressure, volume equals nRT. And to say if we put initial pressure, initial volume, and initial temperature, and then recognizing that pressure, volume equals to nRT again, we would have final pressure, final volume, and final temperature. And I think I was saying this last week on these videos, that when you have something like this, try to put the things that change over on one side of the equation. And usually it's my left. So initial pressure is going to change. Volume is going to change. Temperature is going to change. But the number of moles and the R does not. And the reason that's useful to then write the things that don't change on the right-hand side is because then if you do the same thing in the final scenario, these things that don't change can just be set equal to each other. And so you have initial pressure, initial volume over initial temperature, then would equal final pressure, final volume over final temperature. And that's one way to do that. Maybe I won't spend much time here, but we could do something like this. Remember, this is adiabatic, which means pressure times volume to a factor of gamma is equal to a constant. But if we substitute in right here for pressure, this ideal gas law, we would get an nRT over V, and the T would be left over. Then the volume would be gamma minus 1 because the volume down here. And then the R and the T can be merged with this constant. And so another way of saying the adiabatic process is to say temperature times the volume to the gamma minus 1 has to equal a constant. So we could do something like this. We could say the initial temperature times the initial volume raised to a power of gamma minus 1 would be the same as the final temperature times the final volume to gamma. And that would be just doing the adiabatic process that we just did in A, except instead of focusing on the two variables, pressure and volume, I'd be focusing on the two variables, temperature and volume. And anyways, but I think at this point, that's not the best direction to go. This probably is a little easier because it doesn't have the exponents, but that's just, I'll say this carefully, just math. And so what if it's exponents? But I have noticed that students, struggle a little more with the exponents. So that's why I would say, well, maybe since we don't need to do this method, we can do this method without the exponents. It just has more variables, but we know all these. In fact, I'll put them all in here. We know the initial pressure was 101,300. We know the initial volume, which we calculated back here on page 1, was 2.45 times 10 to the minus 4. We know the initial temperature because the problem says 27 degrees Celsius, although let me be very careful and clear that the ideal gas law is written on the Kelvin scale. So no matter what they give you, you need to put it in on the Kelvin scale. And 273 plus the 27 they give me is 300. So the initial temperature is 300 on the Kelvin scale. Now, the final pressure, of course, is what they gave it. Of course, they gave it in gauge pressure, but that was that 901,300 pascals. The final volume is what we did back here in step A. So that's the 5.14 times 10 to the negative 5. And then, so the only thing we don't know here in part B is the final temperature. So let's get it. All right, so let me grab my calculator here. And maybe I'll do the left-hand side here. So 101,300 times 2.45 times 10 to the negative 4 divided by 300. And so that is the number on the left-hand side. Let me just merge these over there. So if I were to move these over, I would say divide by 901,300. Then I would also say divide by 5.14 times 10 to the negative 5. And of course, what that would give me would be 1 over the final temperature. So if I take advantage and hit the reciprocal key again, I get a final temperature of, it's like 560. Now that's in Kelvin. The general kind of unspoken rule is to give answers in the same units that were given. So they gave temperature in Celsius. So let me then subtract 273 and call it 287 degrees Celsius. And so there would be the new temperature. Oh, now I got 87 and I'm going to say, I'm looking at the wrong one. Okay, let me scroll down. Yeah, so the author gives 560 Kelvin and then doesn't say what that is in Celsius. But I think the general approach should be to write this in Celsius. Oh, and I see that he did use the exponent one. So he went ahead and went this direction on it. I mean, anyway, so glad I mentioned it. But I do think this might be a better approach. Okay, and then finally, there was a C. Let me read that C. That C kind of was sounding a bit particular. And a lot of details about steel and warming it up here. And so C says, what if the bike pump is made of steel and has an inner wall that is 2 millimeters thick? Assume that the 4 centimeters of the cylinder's length is allowed to come into thermal equilibrium with the air. Now, let me pause right there. I think this is what it's saying. If I were to redraw this bicycle pump, now that we have compressed it, what if you compressed it and just held it there? So in this case, the cylinder, the piston, is pushed nearly to the bottom, and it sounds like they're leaving just 4 centimeters above the bottom. Because as you did this downward push, you took your hands and you pushed down on the bike pump, you are going to do a lot of work on this gas. In fact, going back to B, I hope you see how warm this air is going in. This is warm air, 287 degrees Celsius. It's really hot. And so that's the air going into the bike tire. And the reason it got so warm, well, is because the molecules were going so fast. Why were they going so fast? Well, right back here, this adiabatic process, they're going fast, not because we added heat to it, but because we added work energy to it. We actually pushed on those molecules. So they're going fast because we hit them. I mean, this would be like similar, like taking a baseball and hitting it with a baseball bat and go, okay, why is the ball going so fast? Well, it's going so fast because you hit it with the bat. That's why it's going so fast. And so the same thing here. This piston goes down and hits them and makes them go really, really fast. And the energy it gains is the energy by work, not the energy by heat. So the adiabatic process, I think sometimes when beginning students hear, hey, no heat, they think no temperature change. And I want to emphasize that is not correct. Heat is just one type of energy. You can give it energy by doing work to it. And that's what happened here. And that's why the temperature went way up. It was at a little above room temperature at 27 degrees Celsius. And now it is really hot. And if you've ever worked with a metal bicycle pump, you know how hot this can get. You just pump on it, and as soon as you touch it, it's just hot. And we have some scuba tanks that we compress air in our lab, not for scuba, but just to have the compressed air for other reasons. And, we take them down to the Marine Tech down under the bridge. I don't know if you know that, but there's a big hyperbolic chamber and a compressed air. Anyways, so they'll fill them up for us. And it's fascinating because they compress them to over 300 or 3,000 PSI. And the thing just gets so bloody hot that they put it in a bath water. And so they submerge it underwater and say, okay, let's fill it up, because if we don't, we're going to melt the container here. It gets so stinking hot. Well, 287 is not going to melt still, but it's going to be hot. So your bicycle pump's going to get really hot. And then sadly, you'll go check the pressure and it'll look good. And then you'll put the cap on and everything. And then once the tire cools down, the pressure's a little bit on the low side. So I know with my bike tires, I always give them a little above what they're designed to, because I know they're going to cool down. But hopefully not too much that I damage the tire or anything. So, but I know it's going to cool down. Although they're going to stay pretty warm when you're riding them, so they get right. In fact, that's what I kind of like about these modern cars. They got at least my car's got a little pressure gauge now. The tires have a little radio transmitter. It's kind of cool. I can get in the morning and I always look at the tire pressure and oh, look, down to 32. I start driving. 33, oh, there it goes. 34, oh, there it goes. 35, oh. Okay, 35. That's what's supposed to be. Okay, look, oh, it's gone all the way to 37. And so I never known until recently. I just got this car a year and a half ago. So how much it really changes when you're driving. But now that I've got gauges, I can watch it. Anyway, that's a side note. So let's get back to this fun problem here. And so I think C is kind of a throwback to last chapter because it says the pump is made out of steel. It has an inner wall that is this thick. Assume that the bottom 4 centimeters of the cylinder length is allowed to just kind of sit there. So it's kind of like you push down on the bicycle pump and you're just going to hold it there. And once the air gets really warm, then that energy is going to transfer to the metal walls of the bicycle pump. And so now the metal is going to get warm. Of course, in the process, the gas is going to cool down. So my process here is to say, let's do like last chapter and just say the sum of the Q's is equal to 0. And maybe this is overly idealizing it, but the gases in the pump are really hot, as we said, 287 degrees Celsius. And they then are going to warm up the walls or the material of the metal pump, and thereby the gas inside cools down as the metal warms up. And so this is an exchange of energy. So I'm going to go Q1 plus Q2 equals to 0. The Q1 being the air, and so the air is going to lose some heat energy. And the Q is going to be the steel. It's going to gain the energy. Now, of course, be real careful with that phrase, adiabatic, because we started this process and it said the process was adiabatic, but they don't mean this part is adiabatic. And I hope that comes across. What they're saying is the pushing down is adiabatic. And so you push it down so quickly, and that's why we did the adiabatic process in A and could have done it in B to get the temperature. But then as you just hold it in position, then there is time for the heat to flow from the hot gas into the walls of the container. And now we're not talking about adiabatic anymore. Okay. In fact, I would say we're talking about isovolumetric. That is, volume of the gas is held constant. They're saying that you just hold it there at that position, and the gas inside the pump cools down. There is an exchange of energy. This is not adiabatic anymore. What is it? And it is, I think, constant volume. At least based on the information. They just say 4 cylinders and they imply that it stays there. I realize that probably in a realistic world, somebody would probably just kind of lean on the pump and they would probably hold it with the same force. And as the gas cools down, the piston would go down a little bit. So it wouldn't be constant volume as much, it would be constant pressure. I think it may be a real scenario of somebody doing this. But the way they've described the words, I'm going to read into this that this is a constant constant volume scenario. All right, so taking my Q for the air at constant volume, I'm going to write NCV delta T. And taking the Q for my solid material, this is where we have to throw back to last chapter. I'm going to write that as NC delta T. Now let me pause, because one thing that can get easily overlooked because we do so much in these last 2 chapters is, did you notice that the way I calculate the change in thermal energy for a gas is I'm using the molar specific heat. See the N? But the way I calculate the energy for a solid or a liquid, I use the specific heat. So keep that in mind. The specific heats are very useful, but they're really more for solids and liquids. We don't really like to use them for gases. Not that we can't say the equivalent. The problem is, though, with a gas, it depends on how you warm it up. Do you warm it up with constant volume, or do you warm it up with constant pressure? And it's just more useful to look at the molar specific heat. And so my little warning for you guys is, because students often confuse specific heat with molar specific heat. And then the molar specific heat often gets confused with constant volume versus constant pressure. All right, so again, notice for the gas, I'm using molar specific heat at constant volume. And for the solid, I'm using the specific heat. Okay, so now I can kind of put in my numbers here. Now, I don't have the number of moles directly given. So maybe I need to pause for a moment and do that. Remember, PV equals to nRT. So if we put initial pressure, initial volume, initial temperature in our equation, we can get the number of moles. So let's see, the initial pressure was 101,300 pascals. The initial volume, and I need to go back to page 1 here. That initial volume was 2.45 times 10 to the minus 4 in cubic meters. N is what I would like to find. R is 8.31. If you do it in units of joule, mole, Kelvin, which is great because a Pascal times a cubic meter is a joule. And remember, they said the initial temperature was 300 Kelvin. Actually, they said it was 27 degrees Celsius, but I'll say it again. You want to make sure you have that on the Kelvin scale. And then the Kelvin. So the units here are going to come out for N to be in the number of moles. All right. So grabbing my calculator here, this is the 101,300. This is the 2.45 times 10 to the negative 4. This is then divided by 8.31. This is then divided by 300. And it looks like 0.00, well, I'll just round it, 0.0100 moles. And so about 100th of a mole. Okay, so I will need that to feed into here. Oh, and as long as I'm doing that, maybe I also should ask myself, how much mass of steel do I have? Because the density is mass divided by volume. And if you think about, maybe this would be a good time for a little color. But if you think about the original drawing back here, we have kind of this cylindrical piece of metal that's hollowed out on the inside for the air. And so we got to figure out what the volume of that is, and then look up the density of steel, and that's going to tell us the mass of the steel. So this is kind of like a throwback problem to densities, which really is like chapter 14 of our book. So I'll probably have to go back to chapter 14 and look up the density of steel. And so I will do that. I guess first I will write this as mass is then density times the volume. Maybe now would be a good time to go look up the density. I want to say I can find it in chapter 14. I'm sure I can find it on the internet too. Fluid dynamics, densities, measure. Maybe I lied. Densities of various materials. Okay. Substance and copper, aluminum, gold, ice, iron, lead. Okay. No steel. All right. So I'm off to the internet. All right. Let me just type in here density of steel. Oops, too easy. All right. So they say the density of steel is 8 points. So let me do the kilograms and meters. So 8,050 kilograms per cubic meter. No. It really depends on what units I'm going to find the specific heat in. And I bet I'm going to find it in grams. So I'm going to go on a limb here. Let me do the one that says grams. So 8.05 grams per cubic centimeter for the density. Let me go down that direction first, and we'll see if it gets me into trouble. But I think the other one will be more of a trouble, because I know that our specific heats in the last chapter, chapter 20, were written in terms of how many grams, joules per grams. So I really think I want my mass in grams at that point, and then they cancel off, so I can get my energy in joules. You'll see that here. All right. So anyways, there's the density. So now I need to get the volume. And then to get the volume, I guess I'm going to go like this. Pi times radius, I'll call it the bigger radius 2 squared minus pi radius r 1 squared times the height. This would be the volume of something that would have a hollow container in the inside, right? There would be where you would get the area of the base of the container, and that's the difference between two circles. So you take the bigger circle and you subtract the little circle. And then you go up some height h. So if I do this right, it's 8.05 grams per cubic centimeters. Why don't I just factor out a pi from each of those? Now, they said the inner diameter, maybe I'll put that over here. The diameter, and this would be diameter 1, was 2.5 centimeters. So if I cut that in half, that's 1.25 centimeters for the smaller one. So I'm going to put that over here, 1.25 centimeters squared. That's the small one. I just wanted to confirm that. Let's see, what did it say? Inner diameter is 2.5, yeah. So then they go on in part C, it says the pump is made out of steel that has an interwall that is 2 millimeters thick. Okay, so 2 millimeters added on to this radius, because again, the outer one would be the inner radius and then plus the thickness of the metal. And they say 2 millimeters, I'm going to write that as 0.2 centimeters. So this is 1.45 centimeters squared. So that's the outer radius minus the inner radius. And then the height they gave me as 4 centimeters. And I'm, again, liking the units here because this right here is going to be cubic centimeters, canceling with cubic centimeters, and I'm going to get my mass in grams. So let me come over here and say, all right, let's calculate this number. So 1.45 squared minus 1.25 squared is that number. As long as I'm here, I'll just go times 4 times pi times 8.05. And this looks like we have about 54.6 grams of steel. All right, so that was a throwback to Physics 121 and densities and stuff. And calculating the number of moles was kind of a throwback to last chapter. All right. Well, it's a long problem. Either that or I'm talking too much. Okay, so all the way to page 4 here. Now I can finally rewrite this equation. I'll just rewrite it on my paper here, but the number of moles times CV delta T plus the mass times the specific heat times delta T equals to 0. And so keep in mind this up here was the loss of energy from the air, and this right here is the gain of the energy, the heat energy into the steel. All right. So now I think I can finally put in my numbers. The number of moles is 0.01 moles. The specific heat of air at constant volume. Well, let me say it again. I said it a long time ago, but it was the same problem. Way back in part A, was page 1 here, right? We said this factor of gamma is the ratio of the molar specific heat at constant pressure with constant volume. And the way you get it back here is you look at the number of degrees of freedom. And so if it's diatomic, it has 5 degrees of freedom. So 5/2 R is the molar specific heat. So I'm going to put 5/2 R. The change in temperature then is going to be final temperature minus the initial. Now, remember, we're talking about the air, and I also want to be a little careful what I mean by initial, because initial, going to part B, this is really the initial temperature. The 560 Kelvin or the 287 degrees Celsius. So it's not the initial when you started the pumping process, but it is the initial after you push down on the pump and you're holding it there and you're letting the energy transfer out. So it's the initial part of the transfer of the energy. Okay. Now you could argue that should I do Kelvin or Celsius? Here's one other thing to keep in mind. The change in temperature is the same on the Kelvin scale and the Celsius scale. So it doesn't matter whether we use Celsius or Kelvin at this point, whereas that was not true earlier on, right? Earlier on in part B here, we were using the ideal gas law, and what we wanted was the temperature. And the temperature was unequivocally on the Kelvin scale. But some of our formulas have change in temperature. And what's neat about the change in temperature is the change on a Kelvin. In other words, if we go up 2 degrees Well, we don't call them degrees, but if you go up 2 on the Kelvin scale, you go up 2 degrees on the Celsius scale. So that was kind of Lord Kelvin's thinking about the absolute scale, to make the increments the same size. And we could take advantage of that by then just calling this 287 for the initial temperature of the air. And I don't really need to say anything about the Kelvin part of it. All right. Now, the other factor here, the steel, this is the 54.6 grams. And I still have in the back of my mind if I really want this in grams or kilograms. But here's going to be the final answer. I need to look up the specific heat of steel. So let me go back to the textbook. I didn't have luck finding the density of steel, but I'm going to go to chapter 20 where they list the specific heats. They've got a small chart. I don't see steel. Oh, I do see iron. I wondered if I missed it in the density. I should just do iron. Yeah, I wonder. Now I want to go back to chapter 14, but I spent enough time on this one. Let me not go back to chapter 14. But since steel is really mostly iron with a small amount of carbon, depending on what kind of steel you're making, and maybe even chromium or some other things like for stainless steel, I think they want us just to grab the iron one here. So the iron one says 448 iron, 448 joules per kilogram. Okay. Well, I need to fix that here in a second. I was thinking when I looked it up, it would be per gram, but it's not. It's per kilogram. Okay. And then let me just finish the equation over here, though. The final temperature, or the change in temperature, would be final. And the idea being that the steel and the air are going to end up being at the same final temperature, minus the initial temperature of the steel. And I'm pretty sure we can reason that it's the 27 there, that the the starting air temperature and the starting steel, because they're probably sitting outside somewhere a little bit on a warm day, and so it's 27. Anyways, we finally get to the main problem here, which is this conservation of energy. But again, I think a big part of this is to realize the way you calculate the change in energy of a solid and the way you do it for a gas are different. One is the molar specific heat, and then you got to watch out for constant volume versus constant pressure. And the other one is the specific heat. That's kind of the big thing here. Now, before I put any numbers in, let me change this to 0.0546 kilograms, so that the kilograms would cancel with kilograms. And of course, we've got a joule here, but as you'll see, I'll put a joule there, which will cancel off. And then the only thing left is degrees Celsius, which is going to be the final temperature. All right, so maybe a couple steps here to solve this one. Maybe I will take the 0.01 for the number of moles, multiply that by the 5/2. I'm going to write it as 2.5. Multiply that by 8.31. And this becomes 0.20775. Final temperature minus 287. This over here becomes 0.0546. multiplied by 448. And this comes out to be 24.46. Final temperature minus 27 equals 0. I suppose we could do the distributive law next, but I would prefer to divide by 0.20775 there and 0.20775 there, so that this comes out to be final temperature minus 287. And then this is the only place I have a coefficient. So divide by that number up there, giving me 117.74 final temperature minus 27. And then, of course, what's nice about that is now when I do the distributive property, there's only a 1 here, and then this one's pretty obvious. So this becomes 118.74 final temperature. And so I can just take that and then add that 1 to it.
Is
And
that
then this
117 or 107?
What?
That's 117, right?
Yeah, 117. Sorry, did
Okay,
I say?
just wanted to make sure.
Yeah. Sorry. Not sure what I said, but it's 117. Yeah, and then adding 1 to it makes 118. Okay, and then so also doing this distributive property, this 117.74 multiplied by this negative 27. Maybe I'll just put negative 27. Gives me a negative 3,179. And then when I put that with another negative 287, that's a negative 3,466, which when I move to the other side, excuse me, becomes a positive 3,466. So then when I divide it by 118.74, I get a final temperature then of 29.2 degrees Celsius. So it looks like it warmed up really very little. And it makes sense if you kind of think about it, because the gas is warming up a lot, but the steel is now going to absorb that energy. And the steel's got quite a bit of mass and a higher specific heat. And anyways, it's just got a higher what we call heat capacity to it. Now, we did a lot here, so I suppose I better check this answer. But it seemed like a reasonable number to me. What number was this? 20? In part C. What do they have? Oh, is that? Kind of lost at what they did. Maybe, maybe they asked for the change in temperature.
Yeah, it says, what will the increase in temperature be?
Okay, so let's subtract the original 27. Excuse me. I got hoarse here. Maybe I was talking too long on this one. Yeah, and so they got 2.2. Okay, so the increase is 2.2. Nice. Wow. Okay, well, hope I didn't bore you guys too much in that one. That was a heck of a problem. But a good one. That had a lot of pieces to it. a lot of throwbacks to other problems. Yeah, and really showed the adiabatic here. All right, let me miniaturize those two and come back to the Zoom and Risa. I got your questions. I don't see you in here, and I wanted to jump back to yours. Let me see what else is going on here. I might maybe just make it, if she's just waiting for maybe me to record something, I might do that on one of the breaks or something. And yeah, I think maybe I will, especially since that's really all I've done so far, this first one. Yeah. And then Andrew, oh yeah, so that was asked by Andrew, and then it says, also this week I was getting around 0.08 for the specific heats of copper. Did your calculations? Yeah. And I'll say it again for those of you doing the lab, at 0.08 is normal. I know when you look it up, you get 0.092, but 0.08 is kind of our normal value. It just, the metal cools too quickly. And also the heat of fusion is closer to like 70 calories per gram instead of the kind of accepted 81. Yeah. All right. Well, with that in mind, then I think, unless you guys have more on that one question here, let me, at 11:18, let me do this other one from chapter 21, number 16. Hopefully it won't take me nearly as long to do that. And I'll hold off with the 102 questions until somebody from 102 is either here, or I'll just make a separate video, and then maybe we can make the most efficiency of our time that way.
That one might be a little long. That one has all the way up to part D, and also has a what if as well. So if we wanted to hold off, yeah, that works. But if we also don't have anything else to go over, I don't mind it.
Jake, just throw there. Yeah, I think so, Jake. I thought I remember doing a calculation and getting in the 70s. So let me just have you maybe redo that one. We usually get low, not high. So try that one again, or show me your calculations either at Zoom or by email, and I'll run through the numbers too. Well, no, Hunter, I think I'll get started with yours. If it's too long, we'll pause and come back and complete it. How's that, or something?
Sounds good.
All right, so let me just write down here. How about chapter number 21, number 16? And I think I'm still in chapter 21. Okay, good, I am. And number 16, let me just read it here. It says a vertical cylinder with a heavy piston contains air at 300 Kelvin. The initial pressure is 200 kilopascals, and the initial volume is. Take the molar mass of air to be about 28.9 grams per mole, and go ahead and assume that CV is 5/2 R, so diatomic. Find the specific heat of air at constant volume. Now I'm really glad this was asked here, because this will give me a chance to say the same thing on this problem that I wanted and did say on the other problem. Be very careful between NCV delta T, NCP delta T, and MC delta T. They can easily get mixed together, okay? And in the last chapter, we did what I'll call the easier of the two, or three, is that we did the specific heat. The specific heat is a measure of how much mass do you have. And this works really good when you're dealing with solids and liquids, because you can put them on a scale. You can find out how much mass you have. You're not really concerned about how many molecules you have. You just have a number that can be measured by its mass. And so it's measured and it's tabulated, and we look it up. So we want to use the MC delta T for solids and for liquids, not so much the number of moles. For gases, that's different. For gases, because what's happening to the gas is different under constant pressure versus constant volume. And of course, it depends on how many molecules you have, not so much about their mass. In other words, oxygen and nitrogen really behave the same way. They don't have the same mass, but if you have the same number, they behave the same way. So it makes a whole lot more sense to talk about the molar specific heat. Anyway, so there's two subtleties here. One is the molar specific heat, and then there's two of those, constant volume versus constant pressure. And the other is just what we call the flat specific heat. Excuse me. And so those just are easily confused. Now, one is related to the other. In fact, you can kind of see that the specific heat then, and I guess I should have set all these equal to Q, Q, Q. The specific heat would be the amount of heat per mass over a change in temperature, whereas the molar specific heat at constant volume, I'll use volume, but same logic for constant pressure, but this problem asks for constant volume, would be Q over N delta T. And this is where I'm going to take advantage of that. This one says, find the specific heat. And why don't I use this relationship for just a second? So here is the molar specific heat. It has a Q in it, has an N downstairs and a delta T. Watch what would happen if I would multiply the top and the bottom by the molar mass. These two, the N and the capital M, right? The N is the number of moles, and the capital M is the molar mass. So you put those together, you get the mass. So I'll put the Q, I'll put the molar mass still on the top, but I'm going to put an M and I'm going to put a delta T. And then this right here is the specific heat. So if you know one, you can go to the other. Like I said, we don't usually talk about the specific heat for a gas. We like the molar specific heat, but it's not that we can't do it, and it's not that we can't talk about it. And in fact, this problem is trying to show you the mathematical relationship. It's basically saying this, that the specific heat would be the molar specific heat divided by the molar mass. And that's really the crutch of it. So, okay, so to solve this one, I'm going to take the molar specific heat, and since it is constant volume and a diatomic gas, it would be 5/2 R. And did they use the word air here? They didn't, but the 28.9 is the molar mass of air. So I think, and it's diatomic. I mean, their description totally fits a description for air molecules. But this would be, oh, and I do want to be careful here with units. Let me put in a number here in the top. See, because this would be 5/2, and then the R would be 8.31, and the units would be a joule, mole, Kelvin. And so when I divide it by the molar mass, because I have a joule here, I think I really want to write this as kilograms. So let me write this as 0.0289 kilograms per mole. And that way the per mole cancels off, and I'm going to get joules per kilogram. Well, I guess it wouldn't matter. If I left it in grams, I would get joules per gram. And the way I did it is now I'm going to get per kilogram. But if you're going to use joules, you probably don't want to mix it with grams. That just is a recipe for disaster. All right, so I like what I did here. All right, so now grabbing my calculator, this would be the 2.5 for this 5.5 times 8.31. That's the numerator. Then I'm divided by 0.0289, and I get 789 joules per kilogram for each degree Kelvin or each degree Celsius. Because remember, change in Kelvin and change in Celsius are the same. So however you want to write that would then be the specific heat for this, what appears to be air based on the number. Yeah. All right, now let's go to B here, where B says, suppose the piston, actually, you know what? Check that answer. What was that, number 16?
Yeah.
16, they got, same number, but they wrote it in kilojoules. Okay. All right. Moving on. I don't know why they chose kilojoules. Wasn't my go-to. Okay. So then in B, it says, calculate the mass of the air in the cylinder. Now, I'm going to need to come back up here since I kind of forgot what they gave me, but it says here that we have a heavy piston containing air at, okay, so I've got an initial temperature of 300 Kelvin. It's at an initial pressure of 200,000 pascals and has an initial volume of 0.35 cubic meters. So that right there, thinking about the ideal gas law, would be a perfect recipe, since they gave me 3 things and there's 4 in the ideal gas law, to figure out how many moles I have. So N would be PV over RT. So taking those numbers, 200,000 pascals and a volume of 0.35 cubic meters, dividing it by R, which is 8.31. And now remember, this is joule over mole Kelvin. Then a temperature of 300 Kelvin means that in the top, where we got a Pascal times a cubic meter, that's a joule canceling with that joule. We got a Kelvin canceling with a Kelvin, and when we flip over, we get units of number of moles. As we should. So our unit analysis seems to be working right. So the number of moles would be 200,000 times 0.35 divided by 8.31 divided by 300. And so, wow, 28.1 moles. Oh, this is quite a few moles in here. And I guess we are higher than atmospheric pressure and a pretty good volume. Okay, so that's how many moles we have. Now, again, the problem said calculate the mass, but again, this is where molar mass comes in. See, if you want to get mass, you take the number of moles and you multiply it by the molar mass. So in this case, I have 28.1 moles. And if I then multiply it by the 28.9 grams for each mole, I'm going to get the mass. in terms of grams. So 28.1 times 28.9, almost the same numbers. Give me 811.5 grams of, I guess this is air. They don't really say here.
Yeah. Yeah, I think it might be air on there.
Oh, it does say containing air. Yep. Okay. Good. And right there in the first line. All right. Well, then C says, suppose the piston is held fixed. Okay. So now there's an important statement right there. Don't overlook that. That's constant volume. All right. They're dealing with a gas and constant volume, and that tells us a lot. We need to know that. All right. So suppose the piston is held fixed. Find the energy input required to raise the temperature of the air to 700 Kelvin. Well, again, let me just write down that NCV delta T equals the Q. Now, I guess we started this talking about the difference between the molar specific heat and the specific heat. And then talking about when you're dealing with a gas, you want to just keep an eye on, is it constant volume or is it constant pressure? So they made it very clear. Well, maybe not very clear. They could have made it clear by saying constant volume, but that's just too easy. That's just a dead giveaway. They just say the piston is held fixed. And so you have to kind of mentally see that piston in there. And then the movement of the piston changes the volume, and we don't have a change in the piston. So we don't have a change in volume. And that's how we know it's constant volume. Okay. But anyways, the held fixed, just how much energy. So now I've got the number of moles here. This is the 28.1 moles from part B. The molar specific heat at constant volume is the 5/2 R. That was not only given, but even if they would have just said air, you should know it's 5/2 R, because you know air is almost, all diatomic. It's just under 80% nitrogen, just under 20% oxygen. And so 99 point something, big number, is all diatomic, which is 5 degrees of freedom. So they were extra nice by telling you it was 5/2 R, but don't be surprised if in other problems or even on test, it just says air and like, oh yeah, it's air, it's diatomic. Now, all right, so there is the molar specific heat. And then the change in temperature, well, we're trying to warm it up to 400, and I believe we're starting at 300. 300. So that's a change of 400. So that's just a matter of plugging some numbers in here. So 28.1 moles, 2.5 times 8.31 for the 5/2 R. And then times the 400 that we warm it up, and that'll be our Q, and that is the 233,511. And I did my units in joules per mole per degree Kelvin or Celsius, so it comes out to be joules. And maybe this would be a good one to write as kilojoules, or 233.5 kilojoules. Like maybe I should check what the author does. Yeah, they get 233 kilojoules. Good. All right, and then neither of those were long like that other one, but there is a what if. Assuming again that the conditions of the initial state, okay, and assume that the heavy piston is now free to move. And again, that's what you want to catch, right? It's free to move. We're dealing with a gas, so it's still molar specific heat, but it's free to move. So in other words, the pressure stays the same. Find the energy inputted required to raise it to 700. So this is really kind of the same basic calculation, except what is different, and notice then we will get a different number. And by the way, notice we will get a bigger different number, is that this is constant pressure. And the reason it takes more energy at constant pressure to go up the same 400 degrees is because you have to give it energy to make the molecules go faster. But at the same time, those molecules are then lifting up that piston, and they're also lifting up the Earth's atmosphere. They're pushing back on it. So they're like giving up some of their energy. I like to say it this way. If you have a 5-gallon bucket that has a hole in it, and you want to fill up a 5-gallon bucket, you got to put more than 5 gallons of water in there, because by the time you get all 5 gallons filled up, some of that water has leaked out, maybe 2 gallons worth. So you've had to actually put in a total of 7 gallons in order just to have 5 gallons in your bucket. And the same thing's going to happen. If I'm going to warm this up right here to 400 degrees, the same thing that I just did in C, I'm going to have to put more energy into it, because in the process of trying to make those molecules go faster, the energy's leaving. These molecules are lifting up this piston. They're doing work. All right. And so now I need, of course, the number of moles, the 28.1. And I also need the molar, the constant pressure molar specific heat, which the easy way to remember that is it's always 1R bigger than the constant volume. So the constant volume has the number of degrees of freedom, so 5/2, which is, you add 1 to that, you get 7/2. In other words, this is 2.5. You add 1 to it, you get 3.5. All right. And so now grabbing the calculator, I might even be able to, I don't know if that's easier than retyping it, just change the 2.5 to a 3.5 and get 3, well, round it to 27 kilojoules. 1, 2, 3. So 327 kilojoules. And yep, got the same number. And so again, notice it's bigger. And yeah, another good one. Really good one.
Thank you.
Awesome.
Yeah, the first part of that one is what I had a hard time doing, was manipulating the equations.
Yeah. All right. Hey, well, it's a little bit after our break time, so why don't we take our break? We'll come back with more questions, and I'll work on maybe the 102 questions. Might see some people from 121 in their priority time coming up. We'll see what happens. So, all right. I'll see you guys soon.